Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is the second video in a series on the Law of Cosines, and you should have already watched the first one, which is just the theorem and proof of the Law of Cosines. And now we are going to go ahead and use the Law of Cosines to solve triangles. I highly recommend that you watch my Law of Sines videos prior to watching this if you haven't done so already, because the techniques that I use to solve triangles using Law of Cosines are incredibly similar to those that I use for solving triangles using Law of Sines, or vice versa, whatever I just said. So anyhow, in my Law of Sines videos, I had mentioned that if somebody hands me information about a triangle, in this case, they're saying just solve the triangle, but sometimes they say sketch the triangle and solve. No matter what they say, I write down a table of values, a table of angles really, and then on the second column, it'll be the table or a column of sides. So I have angle A, B, and C, and then side A, B, and C. And then I fill in the given information. So angle A was given to be 70 degrees, side B was given to be 60, and side C was given to be 30. If you've watched my video on the Law of Sines, you will know that you can use the Law of Sines if any of these rows are completely filled. But here, none of the rows are completely filled. This means you must use Law of Cosines. So I am going to write here right now that we're using the Law of Cosines. Again, because we do not have a complete row in that table. The second thing I need to mention, and this is so critical that I am going to go ahead and mention it off to the side here. And actually, now that I think about it, I'm going to wait until we get through a little part of this first, and then I'm going to mention the super critical piece of information. So let's go ahead and make a complete row. That's our goal. So Law of Cosines to make a complete row. That's the main idea here. It's just to complete a row. Once we get a completed row, you can then switch to using Law of Sines, which is a much faster and more efficient method than using the Law of Cosines. One thing I should say there is a caveat to using the Law of Sines you have to be very careful of. I'll mention that as we get there. So Law of Cosines to make a complete row. Well, we're given the angle A, side B, and side C. We would like to find this missing side A. Well, to do so, I will just think of the Pythagorean theorem. Side A squared should be something like side B squared plus side C squared, but not exactly, because this is likely not a right triangle. So we'll make an adjustment. Minus 2bc times the cosine of angle A, which is, by the way, the angle opposite this side over here. That is the Law of Cosines. Now, just inserting the information they've handed us, let's go ahead and do that. Let's see, a squared is equal to, this is more of just a plug and chug method. I love the Law of Cosines just for the simplicity of it. Even though it looks terribly difficult, it actually is not. It's a very easy law to use. So there we go. We filled it out. All of this information is just stuff we plug into a calculator. And so I'm going to take the square root of both sides. If you happen to be in a class where your instructor requires that you not use a calculator for exams, and that would be like my students, I do not allow calculators on exams, I let them know, leave your answer in exact form. Exact form is what you would get before you, or I should say what you would arrive at before you would grab a calculator. So basically, what I've finished writing here is considered to be a correct answer for A, the side A. So that would be an exact form. Of course, this is more like a lecture, and then you're probably working on a homework. So we'd like to get an approximation for this, since we're allowed to, on a homework, use a calculator. So I'm going to go ahead and hop over to Desmos. And within Desmos here, I'll just do the square root of 60 squared. Let's see, what is plus 30 squared. And then minus 2 times 60 times 30 times the cosine of 70. And notice I am in degree mode here. So that's critically important that you know that you're working in degree mode when you're dealing with degreed angles there. And I'm also going to go ahead and say that A is equal to that. The reason why is because if I only save on my piece of paper the 57.2, let's say I'm just asked around to the nearest tenth, I don't want to use that rounded value for future computations. So it is very important that if you are allowed a calculator, you save this value. Store it as a variable or as a parameter, A, for example. So we're back here. I'm going to go ahead and fill that information into our table. And so again, this is approximately 57.2. That's the length of that side. Now from this point forward, you do not need to continue using the law of cosines. You're more than welcome to if you want to, but I would highly recommend not doing that, just because it's really, really terrible if you do that. So instead, I'll use the law of sines. The law of sines you can use if you have a completed row, which we do now. We have a complete row. However, remember, that side A is an approximation, so you definitely want to use the longer decimal expansion when you're computing using that. All right, so let's go ahead and talk about the caveat when you're going to use law of sines. Law of sines, and I'm going to write it off to the side so that we have it in permanent ink here. So here's what I'm going to go ahead and copy and paste for all future pages. And it says, once you have a complete row, so we use law of cosines to complete a row, you can use the law of sines. However, if using law of sines to find a missing angle from this point forward, which is, by the way, what you're almost always going to do after using law of cosines, you're going to use the law of sines to find a missing angle, then you must do so for the angle opposite the smallest remaining side. That is, if you take a look at the rest of the information, I could technically use this completed row to help me find that missing angle or that missing angle. I'm highly recommending that you find the missing angle opposite the smaller of the two remaining sides. Now, I don't want to just say that and then have you digest that and memorize it without some level of understanding. So let's just quickly try to develop a level of understanding, because it's actually pretty easy to understand why once I explain it. When you use the law of sines, you're going to use a sine inverse at some point to find the angle. And if you use a sine inverse to find an angle, let's just say we go sine inverse, and we're using sine inverse on some expression, and let's just pretend we want to return angle B, this angle right here. Well, the sine inverse, we know from our material we've gone through in trigonometry so far, sine inverse will only return angles between negative 90 degrees and positive 90 degrees. And to be honest with you, in a law of sines or law of cosines problem, you're dealing with positive ratios. In other words, positive numbers. Your sides are all of positive lengths. And that means that the sine inverse is not going to return anything less than 0 degrees. So really, the sine inverse, when you're using law of sines or when you're working with any application, the sine inverse will only return acute angles. It actually won't even return a 90-degree angle. It's going to only return acute angles, less than 90 degrees. And the problem is, that side that you see there, that's opposite, or this side that's opposite the angle we're currently thinking that we should find, is the largest side, which means it could be opposite an obtuse angle. That angle could be greater than 90 degrees. And by using the law of sines or sine inverse to find that angle, we would never actually get an angle greater than 90 degrees. So this is why I say you should always use the law of sines when finding the next angle. You should always use the law of sines on the angle opposite the smaller side, because you can guarantee that the smaller side will be opposite an acute angle. You can't have two obtuse angles within a triangle. You can't have two angles at 90 degrees or greater within the same triangle. So if B is obtuse, greater than 90 degrees, then C is guaranteed to be less than 90 degrees. And because we're using a sine inverse, and sine inverses are only in these situations going to return angles between 0 degrees and 90 degrees, you'd like to stick with a guaranteed win. And we'll have a guaranteed win by using sine inverse to find the angle opposite the smallest remaining side. There you go. That's the real reason why you use sine inverse, or the law of sines, on the smallest remaining angle against the smallest remaining side. So I'll use this row and combine that with the law of sines to find this smallest remaining angle. That's a good logical reason to use that, right? So we know by the law of sines that the sine of angle C is to side C as the sine of angle A is, which is 70 degrees, is to side A. Now remember, this side A here is actually an approximation. I'm not going to use 57.2 when I grab a calculator. And I'm going to go back to Desmos, and I'm going to use the exact value of that, which is saved in Desmos for me. So multiplying both sides by 30, we get that the sine of C, which is not how you spell that, we get that the sine of C is equal to 30 sine of 70 degrees. And this is, again, being divided by, you know what, I'll just call it side A, because I know that I'm going to go use the A in Desmos. And then I'll take the sine inverse of both sides. So angle C will definitely be the sine inverse of 30 sine of 70 degrees divided by side A. Again, I could have written 57.2 there, but to be honest with you, that would be a poor approximation. So let's go over to Desmos and find out what this is going to be. So here I am. We're going to just type in that angle C, capital C there, is equal to the arc sine of 30 times the sine of 70 degrees. And I'm going to divide that by A. Notice that's all I had to literally do. Just type the letter A in there. And I get that angle C is 29.5 degrees, roughly. So I filled that out. I'll go ahead and go to my table. I'll use a different ink. I'll just stick with green for the ink that represents what we've calculated. So this is going to be roughly 29.5 degrees. And obviously you can approximate B here by taking 180 minus 70 minus 29.5, because you only have 180 degrees in an entire triangle. I could go over to Desmos and compute that out, and I will. And it's roughly 80.5 degrees. Notice we have the entire triangle done. I didn't bother drawing it out because I don't want to. But you could, if your instructor asks you to, you could totally draw this out if you want to. I generally find that drawing this before finding all the values is moot. It's not really the best idea to do because you have no idea what all the angles are. You could draw it after if you really want to. The other thing I want to say here is if you've already gone through, which you should have, the law of sines, because we're using it, so you should have already gone through it, you will notice that you should recall that with the law of sines, there's the ambiguous case. If you followed my advice here, when you use the law of cosines to first fill out a row, and then you switch to the law of sines to find the angle opposite the smallest side, you will never have an ambiguity in these styles of problems. So you don't have to worry about the ambiguous case here. That's just a heads up. Let's go ahead and try this example just to really kind of cement the idea. You should go ahead and pause the video and try it yourself. I'm going to go ahead and just fill out the table here. Angle A is not given. Angle B is 25 degrees. Angle C, which I'm using capital there, is 98 degrees, which by the way tells me that I can easily and quickly compute what angle A is because, well, they've given us two angles. So that ends up being 57 degrees. And then we have side little a. Did they give us that? Yep, 1,000. And then side little b and side little c. Notice in this case, we don't need to actually use the law of cosines because we have a complete row. The law of cosines is not always necessary. Try to use the law of sines if you have the option to. And in this case, I definitely have the option to use the law of sines. If you want to, you can use the law of sines to find the side length opposite the smallest angle. It actually doesn't matter when you're finding side lengths, which one that you use. But if you want to just stick with one piece of advice and always use the law of sines on the smallest angle or the smallest side, then go ahead and do that. It doesn't hurt. But this is I started this as a law of cosines thinking it would be, but it turns out you don't need it. And if you don't need the law of cosines, don't use the law of cosines. Use the law of sines. That's just a much faster and cleaner rule to use. So by the law of sines, we know that side B is to the sine of its opposite angle, 25 degrees, as side A, which is 1,000, is to the sine of its opposite angle, which we were easily able to compute to be 57 degrees. Multiply both sides by the sine of 25 degrees, and we get this beautiful result. B is 1,000, sine of 25 degrees, all divided by the sine of 57 degrees. So this just becomes a law of sines problem. And I'll quickly compute this. It's approximately 503.9. I'll just write that in here. And remember, you don't, if you didn't watch my previous video on the law of sines, if you're just not one of my students, but instead you just wandered upon this, happened upon this video on YouTube, I said in a previous video that you should not use an approximated value if you have a choice to get another value. So I'm not going to use this full row, the second full row, to help me find the third full row. That would be a bad idea. You want to use a good clean row to help yourself find values. So I'm going to use that first row again to help me find that unknown C. And that's just because you'll suffer from round off error if you end up using approximated values. So in this case, we have side C is to the sine of 98 degrees, and you know how this goes. So you could fast forward this if you want to. Obviously, you always have that choice in life. Is equal to side A over the sine of angle A, and multiply both sides, and you get the following. And then I just grab my calculator. By the way, notice that the setup for side B and side C share quite a bit in common. They have both 1,000 in the numerator and both the sine of 57 in the denominator. The only thing that's changing is that angle of 25 degrees. We're changing that into 98. And this becomes roughly 1180.8. I don't know the units and I don't really care. They didn't really hand me units, so that's not that big of a deal. And also notice that I'm arbitrarily just rounding to the nearest tenth. Please be aware there could be instructions that tell you to round to the nearest whole number or the nearest hundredth, right? So just pay attention to the instructions within the problems that you're dealing with. Let's go ahead and solve this triangle, and notice something weird about this triangle. When I draw out my table, angle A, angle B, angle C, notice none of those angles were given. Side A was given, and side B, and side C. So you can see there's not a complete row, and that implies we are going to use law of cosines. We're forced to. So this is kind of the rule of thumb when you're using law of cosines and law of sines. The law of cosines is going to be kind of your last ditch effort. You only use it if you don't have a complete row. If you do have a complete row, you always use the law of sines. It's just a good idea. To be honest, you could use the law of cosines even if you had a complete row. So I don't want to lie to you and say you can't, but the law of sines is just much faster to use. Law of cosines is just a lot of computational nightmare that can lead to issues. And we honestly have choice here. You could say c squared is equal to a squared plus b squared minus 2 ab times the cosine of c, or any other permutation you want. It doesn't really matter. I will go ahead and use the law of cosines, and I will use it on the largest side. And the reason why I'm going to use it to find the angle the opposite the largest side is so that when I use the law of sines, after I find that angle capital C there, when I use the law of sines, all the remaining angles are acute. So I never run the risk of an arbitrary case. So again, I just want to paste this over to the right. What we said before, which is once you have a complete row, you can use law of sines. However, if using law of sines to find a missing angle, which is what you're going to be doing, then you must do so for the angle opposite the smallest remaining side. And that's because sine inverse only returns acute angles. However, if you use law of cosines to find the first missing angle, in other words, if you have been given all three sides and you don't have a full row there, to find the first of the missing three angles, you could use law of cosines intelligently to find the largest such angle. And therefore, the smaller those remaining two angles are both going to be acute. And so you don't run the risk, just in case you forget my advice over here, you don't run the risk of having the ambiguous case. All right, that's a lot of wording. Sorry about that. So here we go. C squared, I'm going to use this formula, C squared is equal to A squared plus B squared, just like the Pythagorean theorem, minus, so here's the adjustment, 2AB cosine of the angle opposite that side C. That's why I chose C squared, because I want to find the angle C. Let's fill in this information. That's 16 squared is equal to 10 squared plus 12 squared minus 2 times 10 times 12 cosine of the angle we just don't know. And as I mentioned in my video on proving the law of cosines, I don't want my students to memorize 6 different formulas. It's just enough to know the one formula, the modified Pythagorean theorem here, the c squared equals a squared plus b squared, and then the modification minus 2ab cosine of c. If your unknown is that angle, start solving for it. You would get 16 squared minus 10 squared minus 12 squared, so that would move all this stuff to the other side. Then you would divide both sides by a negative 2 times 10 times 12, so that would get all of this stuff moved to the other side, and then you just would have a cosine of c. Of course, you could also have just said, well, and then I would take the cosine inverse of both sides, and that would give you the full and complete angle C there. And now you go to Desmos to find out this value. Now, just to let you know, I am going to save that angle C in Desmos because I need to use the exact value, because that angle C is going to complete a row for us. And we have to use that approximated value of our angle C. We're going to use that to help us find the next angle, and so on and so forth. So when you use approximated values, you don't want to round them too much. And if we just save them in Desmos, we won't round them at all. So here we are in Desmos. We're in degree mode. You can see it right there. And I'll go ahead and start typing. We want the angle C to equal the arc cosine of a fraction. So notice I started the fraction first because it's a little safer. 16 squared minus 10 squared. Yes, I know that's 100, but I just want you to see that you don't have to actually pre-compute anything. This is exact form here. And then downstairs we had a -2 times 10 times 12. And you can see that angle that we just found, which I told you is opposite the largest side, so it could be obtuse. And here it is. It totally is obtuse, but luckily there's not going to be an ambiguity here. We have now found the only obtuse angle within this entire triangle. And so now we're very safe to use the law of sines for the rest of the angles. So I've written 92.9, that's the rounded version of it for angle C, so 92.9 degrees. And now that we have a completed row, I'll highlight the completed row now. We know we can use law of cosines. Just as a good habit, I'm going to use the law of cosines, or sorry, I said law of cosines, I mean law of sines. I apologize. We're going to use the law of sines to find the angle opposite the smallest remaining side. Even though in this case, it actually doesn't matter which angle we will go for. It's a good habit to keep. So let's go ahead and use the law of sines there. I'll do the computations off to the left. So sine of angle A is to its opposite side as the sine of angle C, which I'm just going to write as angle C because that's an approximation and I'm going to go to Desmos for the actual value, divided by its side, C. Multiply both sides by 10 and then take the sine inverse and you will get A is equal to the sine inverse of 10 sine of angle C divided by 16. Now let's go over to Desmos. Here we are. I'm just going to go ahead and say angle A is equal to the arc sine of 10 sine of angle C divided by 16. That is angle A. Now remember, there's only 180 degrees in an entire triangle, so angle B is equal to 180 minus A minus C. And there we have it completely filled in on our table. Completely done. So you can see the law of cosines actually isn't terrible and it's very useful in calculus. So it is a good idea that you really study the law of cosines. It does come up in calculus every now and again and nobody's going to remind you of it there. That actually sounded pretty terrible. I apologize for that. Anyway, our last example in this video, let's find the diagonals, or I should say, the diagonals of a parallelogram are 56 inches and 34 inches. And they intersect at an angle of 120 degrees. Find the length of the shorter side. So let me draw a picture of this situation so we can easily see what I'm talking about. So we have this parallelogram, each a parallel side. We have two parallel sides basically, but it's not necessarily a square. And the diagonals of this parallelogram are 56 and 34 inches respectively. So for example, maybe I should have done a different color here. So this green length here, as I muck up my picture, is 34 inches. Double hash meaning inches, and then the long diagonal is 56 inches. And we're being asked, oh, and also they tell us they intersect at an angle of 120 degrees. Obviously there's actually, there's one point of intersection, there's four angles. However, these two right here are going to be 120, and then these, the angles on the other sides are supplemental angles. So, or supplementary angles. So these would be 60-degree angles right here. That's just to let you know. All right. And then find the length of the shorter side. So we want to find this length right here. Okay. So how are you going to find that length? Well, the best way to do this is to grab one of the triangles, specifically this, let me grab a highlighter. This triangle right here is probably the best one to grab. And then fill in as much information as possible. So I'm going to freehand draw this. So we have this triangle right here. This is 60 degrees. This length right here is half of 56. Remember, the red length is 56. They intersect at the center. That's actually part of geometry. So if that's half the length, that's 28 inches. And the bottom length will be half of 34, which is 17 inches. I recommend actually labeling things just to make your life a little bit easier. So I'm going to label this angle A, angle B, angle C. It doesn't really matter how you label them. And therefore this is side A, this is side C, and this is side B. And then I make my table. That's it. So angle A was given to us as 60 degrees. Angle B we don't know. And angle C we don't know. Side A we'd like to know. Side B we know it's 17 inches technically. And side C we also know, which is 28 inches. And our goal is to find that side A. Again, we don't have a full row, but we can complete a full row just by finding that side A. So let's go ahead and do that. And by the way, that's all we need to do. We only want A. So filling out that row is exactly what we want to do. Well, A squared equals B squared plus C squared, but it's not really a right triangle, so we're going to have to modify that. Minus 2BC cosine of the angle opposite side little a, which is angle capital A. And now filling in the information, A squared is equal to 17 squared plus 28 squared minus twice 17 and 28 times the cosine of 60 degrees. At this point, you would take the square root of both sides, and I'll just quickly jot this down. And just to let you know, again, if you're one of my students and I say leave your answer in exact form, you would almost leave it just like this. The only thing that I would like you to do if you're one of my students is to trade out that cosine of 60 degrees for a half, because that's what the cosine of 60 degrees is. And then you could cancel it with that 2 out front. But for our purposes right now, I'm just going to grab a calculator and to find the approximate length of that shorter side. And I get 24.4, and remember our units are inches. So 24.4 inches. And that is the length of the shorter side of that parallelogram within this problem. All right, so there we have it. Sort of an application of the law of cosines, but I actually will have a couple videos for applications of the law of cosines after this. All right, see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.